Hey everyone, how are we doing? Hope everyone is having a good day. Confidence intervals due tonight, so we should probably do some confidence intervals. But how is everyone doing? Is anyone in the chat want to do some work? Maybe I'll send out a reminder, say, hey everybody, we're over here. Let's do that. We are working on assignments. Let's see right here. No worries. We did it during office hours yesterday. I am currently streaming here at 201. And then we'll put yesterday's. If anyone's here, say hey in the chat. I'm just chilling right now, sending out. We are currently live stuff. And here's yesterday, Data Analytics 7. Noel, good morning. Good to see you there. I'm sending out reminders or hellos to everybody. And Data Analytics 7. There's the link there. And here is MuBot is awake. And the visualization playlist. One of my favorites, the visualization playlist. And that's my favorite videos. So we want people to use the playlist if possible. I'm just going to do this a billion times with my hair. Visualization playlist. Hey, Isha, good to see you there. If you have questions, let us know. We'll probably work on some chapter 14 quiz stuff. That might be the most pressing issue. But let us know. Let us know what you want us to work on. I'm going to try to get MuBot to say the visualization playlist. Which has videos going over how to make each of the visualizations. So check that out right there. I've pinned it as the comment, and a lot of fun videos. Try to make each of them a little bit fun right there. So I'm gonna do this one right here. Send this one. Here we go. Help videos. Say more help videos. There we go. The Joker. Find out. Check out the video. So, can you explain to me how do we check the 10% satisfied or not? Yeah, let's go over the intervals, how to make and check intervals. Let's talk about that in general. And so we'll do a section on conditions of a T interval. Let me mark that in the notes. Conditions of a T interval. So office hours over here. Conditions of a T interval. Let me put it in the notes. We are at the 4:43 mark. In Stat 201, conditions for a T interval. Let's do this. Thank you, Dee. Oh, I didn't hit the button. What did I do? Good to see you, Dee, in the chat. Oh, I didn't hit the button. There we go. So these are the conditions for a T interval. Now, there is for the rest of the semester. Oh, enjoy. Have fun. You can say where you're going if you want on vacation, but have fun. Enjoy the vacation. Good to see you, Dee. And I love it that we have people from all the world that I've met and honored that they swing by. And so tell us how it goes. Enjoy your vacation. So with this, the T interval, when do we use the T interval? So when do we use the T interval? We have to know when we use it. What is a T interval? When do we use it? What is a T interval? When do we use it? What is a T interval? When do we use it? Well, if you look at the equation, we get a lot of nice equations right here. Now, they call it X bar. We call it Y bar. We need to take a T break. Definitely. Everything's around here, T at UT. So you can call it X bar. You can call it Y bar. As The Rock would say.
It doesn't matter.
Doesn't matter. So it is the sample mean creating an interval. The plus or minus is the margin of error. So this is the margin of error, MOE. It creates the lower and the upper on the interval. The Z, I'm glad they say the Z is for the confidence level. The N is the sample size. And the lowercase s is the sample standard deviation. We talked about this a little bit last time, that differs from sigma, which is the true standard deviation, like y bar differs from mu, and some people even do mu y bar, or mu y, excuse me, for mean, population mean of variable y. So this is what you're creating right here. You have to know the notation, as Leo always says.
Notation, brother.
I don't think that's notation, brother. It might be. So you have to know your notation and how to find these things for any questions. But we're wondering right now, what are the conditions? So for the remainder of the semester, you'll have two conditions that stay the same. What are the two conditions, Noel, that always stay the same? There's two conditions for the remainder of the semester that if you're memorizing things, they'll always stay the same. We're not in the QQ straight enough, no outliers world anymore. Random and 10%, you are correct. We love randomness. Mubot loves the randomness right there. Random and 10%. So what are these conditions? Well, we know that if you were to find out, do people own animals? Well, maybe if you talk to your friends and you live in the dorms, you'd be like, no one owns animals. That's not a random sample. And they might own animals. I don't know if you can in the dorms, but it wouldn't be a random sample to talk to your friends. That's a convenience sample right there, not random. So random is checked by, so how do we check this? Did we go out and collect random observations from the population of interest? That's how we check it. Did we do that? Did you get a convenience sample? Did you talk to the easiest people to talk to? Yes or no? Hopefully no. If you went out and talked to random individuals, then that's a random sample. Random, maybe you're looking at Pokemon cards and you're figuring out what percent of your Pokemon cards are scratched. I don't know. You know I love Pokemon. And then you'd have to randomly take your Pokemon cards. You can't take the top 10 Pokemon cards you have and be like, wow, maybe it's the ones you use all the time. So random means something like everything is enumerated. You pick random observations. Questions in our class will usually say we randomly selected. My Pearson's a little mean sometimes because they'll say you can assume randomness. What is the 10% condition? It's the less than 10% condition. I call it 10% a lot of times for short, but the less than 10% condition. And what does it mean? Is our sample size less than 10% of the population size? Checked by doing lowercase n over capital N is less than or equal to, less than 10%. We'll never make it exactly. But here's the thing. Not all questions tell you n. You might have to deduce this. So we're doing the t-interval, but I want to hit you with this question. We talked to UT students, and 40 out of 100 like Taco Bell. You know I endlessly talk about Taco Bell. We'll get that Taco Bell sponsorship one of these times. This is a proportion interval because it doesn't deal with the mean. Mr. T is mean if you're doing drugs. And that's how we memorize t-interval is for means. We talked to 100 students, and 40 of them like Taco Bell. Do we pass the 10% condition? This is a proportion interval if we're making an interval from this. So Noel, do we pass it? Why or why not? So think through what you're doing. Well, so this is, so the question on the 10% is our sample size less than 10% of the population size? Checked by doing n over, so you look at what we got to find right here. N over capital N is less than 10%. Not all questions will tell you n, which is population size. So not all questions will tell you that. You might have to deduce this. So what math would you do? You have to think, did I sample less than 10% of the population? So how would we do this? Did I sample less than 10% of the population? So that's what the 10% condition states. Our sample size is less than 10% of the total population. So let's try to identify things in this problem. We need to identify n, lowercase, and n, capital. So what do we have? What do we have? You are right, Noel. And this problem did not tell us capital N. And great job, we'll throw you some Mubot points right there. So in this problem, you were given the sample size, but you were given something else. You were given x. X is the number of successes. So you could find from this p hat, which is x over n, which is not part of what we're doing right now, but would be used later on to make a confidence interval for the true proportion. So in this problem, the thing to identify is our sample size is 100, and then the population of UT is probably closer to something like 35,000, which then you could do the mathematics here, and you could do calculators on the other screen. 100 divided by 35,000. And when you do that, you get less than 0.3%. If you do it by a percent, there's a percent. It's 0.28%. So is that less than 10%? It's way less than 10%. And you could explain to someone, say 100 students is way less than 10% of all UTK students. You could also check this by figuring out 10% of UTK students, which is another way to check it, is times this by 10%, and you would get 3,500. So our sample size is less than this. The body temp on, yeah, you got it, Isha. Let's do that next. So do you see the way to check the 10% condition? You ask, is our sample size less than 10% of the population? You can then look at your sample size in the population to check that. Now, the last condition, we always pause. We put those pause in the chat because you won't always do the same condition. The condition for the mean is going to be what? And I highly suggest checking out Review 3 videos. The condition for the mean is going to be what? What is the condition? And we'll do Isha's question next right here. When doing the confidence interval for the mean, the third condition is what? When doing the confidence interval for the mean, the third condition will be what? And we pause because if you've learned conditions, you might just say one really quickly. But we pause to remember the condition. So what is the third condition for the confidence interval for the mean? Any ideas on that? The third condition for the confidence interval for the mean, there's random, there's 10%. But when we get to the third condition, what will it be? Take a guess in the chat. You can see proportion interval, that's proportions, t-test, which means intervals for the means. Nearly normal, great job, Noel, you are correct. Nearly normal is when we're dealing with the mean. And you can see right here, I start to write them in, success failures for proportions, and then nearly normal is for the means. Chi-squared will be something we'll do later on. But right now we've covered success failure and nearly normal. Success failures for categorical data, proportions, success failures. The mean is t-tests and t-intervals. You can do a t-test or a t-interval for the mean. So with that, you would use the nearly normal condition. So how do we check the nearly normal condition? This is a more complicated one, more nuanced. Well, we should leave pause in there. Let me do this. New page. There we go. I can zoom out a little bit. Cool. Okay. Control-Shift-Enter, new page. And to check the third condition right here, nearly normal, there are multiple ways to check this. 1, does the histogram look mostly unimodal? Mostly modal and symmetric. 2, does the normal probability plot Three, does the goodness and last but not least, oh my gosh, 4. A lot of times, is our sample size large enough? This is what's often done. So that's what's often done. I'm just confused because our sample size is 100 on YouTube, but we don't know how many students is in the Stats 1 class. So it's assumed for all UT students. Assume all UT students, Noel. So assume the population is UT students. So assume the population of interest is UT students. Does that help right there, Noel? So for the 10% condition, which that should probably tell you what's going on with the condition for the visualization, assume it's all UT students. So think about if we'll pass that one. So does that help with that, Noel? Assume it's for all UT students. So when you're doing the nearly normal condition, if you're making, assume it's for all UT students. So it's a large population and you're taking not that large of a sample. So when you're doing the nearly normal condition, if I have a sample size of 800, I could get a distribution that is, let's say, a little bit skewed. So you can see the skew to the right. It's right skew, Monster Man right there, right skew. Yeah, no, you definitely passed the 10%. I'll just flat out say it. You'll say you passed the 10% because I don't want to say the words lest people copy exactly what I say. I'm always worried to say it and then everyone will write exactly what I say. But you pass it. There's your Monster Man with his right skew tail. You can see the high outliers on the high side. So right to the high, left to the low, whatever way the Monster Man's tail goes. And with this right here, you'll notice that we have a sample size of 800. So my answer would be, understand, yeah, exactly. And my answer would be, for the nearly normal condition, the distribution of the mean is extremely normal because with a sample size of 800 and only a lightly skewed parent distribution, we will see a normal distribution of the mean because of the central limit theorem. The central limit theorem is why when we take samples from skewed populations, the distribution of the mean becomes nearly normal. It's the large enough sample size that allows for it to become nearly normal. So you can have a skewed distribution and take a large sample size. This only goes to 25. But when you start to get values of the mean that occur from a skewed distribution, well, what you'll notice is the distribution of means, if we repeat this process, is nearly normal. And the larger the sample size, the more normal the distribution of the mean becomes. Also, the smaller the standard deviation is by a factor of the square root of n. And you can theoretically figure out what this will be by taking the original standard deviation divided by the square root of n. Square root of 25 is 5. And you can see 1.24. You'll notice it's not that, but if I run the simulation longer, it's messing with me. There it is. It's very close to 1.25, but it's 1.24. And running the simulation long enough will achieve that via the law of large numbers. So I love stats because it's basically just how the world works. We've got the law of large numbers, we got the central limit theorem, things like that tell us what we would see from this data, a more normally distributed distribution via the central limit theorem, because a large enough n will achieve a distribution of the means that is more normal than the parent population. So, and the parent means the original data, we are taking from. So this is the original data we're taking from here, but we would have a distribution of means that looks something more like this right here, more normal and tighter. I accidentally drew a little bit of right skew on that because it should look something like that right there. It should be a lot more normal and tighter around the original value of the mean, for which we will make the confidence interval right here to estimate the true value of the mean. So the nearly normal condition, you could mainly, this one is almost normal enough that you could look at the histogram and say, no, it's got a little bit of skew. I would still say via the central limit theorem, the distribution of the mean will be nearly normal because the sample size of 800 is quite large. And with only a tiny bit of skew, we only need a sample size of 25. You can remember those numbers from the last test. And with sample size of 25, we have at least 25, we have 800. So the central limit theorem will kick in and we'll get a distribution like that blue one down there that is nearly normal. Central limit theorem, distribution of the mean will be more normal and tighter by a factor of the square root of n. Cool stuff. Let's do the next question. Noel, I hope that helps out right there. Does that make more sense? We went kind of an in-depth deep dive on the nearly normal condition, just explaining how to do it and how to talk about it. You could also, maybe I should have shown, do you plan on office hours that help with the project? Yes, the project. We should do that next week, Luke. I do have videos, but we should dedicate a whole day to that. The project, when's the project due for early credit? Thank you, Luke, for being here. And we're gonna do Isha's question next. When is the project due for extra credits? We will do a whole day dedicated to it. Might even do a unique stream for it. And then it'll be all recorded and you can be here and ask questions. I love it then. It's due 22 for early. So I think that's a week from Friday. Yep. And I think it's due on like Monday or something for regular. So we will do, I just fade in now all the time. We will do that. Was it Isha wanted? Alright, I'll fall asleep. We will do that. I thought I saw a question. Where is it? Am I going crazy? Can we do the researcher measure body temperatures? Yes, here it is. Researcher measured body temperatures. Okay. I would love that. Awesome. We will get it done. Researcher measured. Speed of light problem is one of my least favorites. It's got so many decimals to carry. Okay, let's go over here. A researcher measured body temperatures. Waist sizes. Oh, there it is. Okay, researcher measured body temperatures. 2, Fallout 3, Stat 201. Feel free to ask any questions. Remember, practice. A researcher measured body temperatures. Okay. So, first off, they're giving us summary statistics. Summary statistics are things like the sample size, because remember that's for a sample. Summary statistics come from samples. Remember SSS, so summary statistics come from samples. PP, population parameters. Those are the things for the truth for everybody. And we will have like standard deviation of a sample. S, we will have Y bar, which is mean of a sample. And here we are. They didn't quite label them that. I wish they did. We're going to label them ourselves here. So some of this will not be used, but we should know how to label things. That was our work we just did. Pause. Okay. So the count is going to be equal to n. That is the number of observations. The mean is going to be Y bar. And you know what I'm going to do? I'm going to chat GPT and say, what is the notation for the median in statistics? I don't know if there... What is the notation for the median in statistics? There we go. In statistics, med x. We got a little... Ooh, tilde symbol over it. Oh. I just learned something. Y tilde. So it's got a Y tilde, it looks like. Some people do the Y tilde. Maybe. So Y tilde, not Y bar, Y tilde. Maybe. Don't quote me on that. And the mid-range, I don't even know what the mid-range is. What is the mid-range in statistics? I never used that. What is the mid-range in statistics? And what is the notation for it? Should ask these questions. Say, what is this? What is this? Okay. Is a measure of central tendency. Central tendency means like the mean or median. Oh, it's... Okay. Oh, wait, but that would be... Oh, that's not going to be the median then. It's the middle of the range, the mid-range. Where's my wow? Just wow. The mid-range is the middle of the range. Like if I tell you students scored from 0 to 100, the mid-range is a 50. So the mid-range is the middle of the range. And I don't know if there's any notation for it. MR of Y, so it's MR. They call it MR. A straightforward abbreviation, maybe, yeah. So it's the middle of the range. It's the middle value of the range. So MRY. No, not Y bar. Stop it. Standard deviation is S. Range is range. And interquartile range is the IQR. Range is the middle 50%. So the range, well, we could actually find out what's interesting was we could find the min and the max from this. So I wish they did questions like that if they're going to give you a mid-range. Because think... if the range is this, then the mid-range would be in the middle of it. So the maximum body temperature is 100, and the minimum body temperature is 97.2. And you'll notice the total range goes from here to here, and thus the middle of the range would be right in here, the average of the two numbers. So that's what a mid-range is. I think I knew that at one point, but then you don't use it, you forget it, and then you're like, oh, that makes sense, middle of the range. Once again, these are not the questions they ask, but we can figure out these things by deducing information. The IQR stands for the middle 50% of body temperatures have a range of 1.04. The full range of body temperatures is 2.8. Okay, and let's go take a look at what they ask us to do now and answer those questions. Check the conditions here for making a t-interval. Now, we need to look at the shape of the data. Now, this is not too skewed. This is lightly skewed, maybe to the right. Sometimes with only a light bit of skew, it can be hard to tell. And so we've got right here Monster Man a little bit. I think his tail's going to the right, but this is not heavy skew. So we were talking just a moment ago on how to check these conditions. And so with the nearly normal condition, we would look at the histogram and see if it's mostly normal, which we might be able to say it passes on that. We didn't get a normal probability plot, which is the plot that shows the line, and if the line or the dots follow the line, it's normal. We didn't get a p-value, which above 0.05 would indicate it's normal, or we don't reject the null that it's normal. And last but not least, we can use the central limit theorem with the large enough sample size, which we did with the last test. And that's what I'd use here. I'd say the sample size of around 52 is more than large enough for some light skew, which requires a sample size of at least 25. So the distribution is only lightly skewed, and with a sample size of 52, which we saw over here in the summary statistics, the light skew is not going to be a problem. I'm assuming that these 10% are there's way more adults than 520. Why 520? Well, we took 52 sample, times that by 10, there'd have to be at least 520 adults for 52 to be less than 10%. So notice I'm kind of doing some reverse ways of solving it, because I can say, well, the sample size is only 52. It's way more than 520 adults. So our sample size is way less than 10%. Was it randomly selected? Boom. That's how you know randomization is met. So yes, 10% is met because our 52 adults is way less than 10% of all adults. Randomization is met because the question states it. Nearly normal is met because the distribution only has a light amount of skew, and a sample size of 52 is large enough such that the distribution will be more normal based on the central limit theorem. Okay. Now we have to create the 95% confidence interval. And this is usually where people get stuck. We need to go to the t-applet to do this. On the t-applet, you always have to give the degrees of freedom. So what are the degrees of freedom? Noel, do you know the degrees of freedom for this? We didn't mark it here. What are the degrees of freedom? For a one sample t with a sample size of 52, what are the degrees of freedom? So on a one sample t, see if someone says it in the chat, df for the one sample t, the degrees of freedom equals n minus 1. So we plug into the formula, 52 minus 1 equals 51. Once again, no, one sample t, n minus 1 degrees of freedom. One sample t means we are looking at one mean. What's the mean of body temperature? Two sample t means you're comparing two means. What's the difference between male and female body temperatures? Mean for male, mean for females? What's their difference? One sample t, what's the IQ of UT students? Two sample t, what's the difference between the IQ of UT students and Florida students? I don't know, I'm partial towards UT, so I hope a lot. That's my impartial opinions. UT's the best. You know I think that. Nothing against Florida. We're just geniuses here. So with that, we need to get the t statistic for the 95% confidence interval. We had the equation a moment ago. We'll go grab it from the other picture right here. The area, it might be, was it a 98% confidence interval? Was it a 98% confidence interval? I can't remember. I think it's a 95. So we have to go to the t-applet, and we're going to pin the t-applet. We'll bring our work back over here. And there's the formula we're going to use. And, oh, they're saying z? Oh my gosh, how did I not notice that? Yours might be 98%. Yours might, let me look at mine again, 95%. So mine will be close to 2.01. Let's go take a look at it right here. We're going to click on the applet. We'll show how to get the t statistic. Whenever you're making a confidence interval, you have to click between, because the confidence interval shows you the area between. I'm going to increase the degrees of freedom just a little bit so you can see 95% of the area is contained between negative 2.45 and 2.45. Now, the degrees of freedom tell you the shape of the t. Notice it's changing in shape. Where low degrees of freedom is a more spread out t, higher degrees of freedom is a tighter t with thinner tails. That's what happens to the t distribution. It becomes more normal as degrees of freedom increase. So we don't type 52, we type 51 because the degrees of freedom, which dictate the shape of the t, are determined for a one sample t by n minus 1. There's other formulas for degrees of freedom, like the two sample t has a different formula. So for one sample t, n minus 1, and there is the t statistic, we will use 2.01. So now that we know the t is 2.01, we go back here and we start plugging in numbers. So 2.01 is the t. That's going to be part of the margin of error. The mean, we can scroll back here to the data, it might be a little zoomed out. The mean is 98.536, and then s over square root of n, 0.6707. Square root of n is 52. Notice we're just taking the numbers. Does that make sense? We are literally just taking the numbers right there. 98.536 plus or minus the t statistic, and I'll zoom up just a little bit so you can see here, s over square root of n. Those are the values we're using. The first thing I solve is the plus or minus to get the margin of error. So I'm going to go right here and solve everything over here in the formula. 0.6707. Well, I don't know square root of 52 off the top of my head, so I have to go find that. Square root of 52. 0.6707 divided by that square root of 52, which I saved, times 2.01, and that is the margin of error, is 0.19. There we go. So now this gives us the estimate and the margin of error. Make sure you know that over here on this side is the estimate of what the truth is obtained from the sample. Everything to the other side is known as the margin of error. And you can see it right here that it says margin of error. I added that in, which is everything to the right of what we estimate the truth to be based on the sample. So we are simply going to add and subtract. It might say to 2 decimals, so I'm going to round this. I'm going to hope it says to 2 decimals. It just makes it nicer. And here's the good. This is basically 0.2. I might be able to get away with just calling this 0.2. Be very careful. I just think this makes this easier to look at. Noel, looking at this now, and we'll see if it works, what would be the lower and the upper of this interval? Think about what you're doing here to the decimals. So adding and subtracting, because I want it to be easier to look at. Once again, you're just adding and subtracting. What would be the lower and the upper using my not so perfect math? I cheated because I changed decimals. I removed decimals off of this just to make it nicer so it is easier to do. A lot of people might be able to do it in their head now, but what would be it? And you can also use a calculator. Nothing wrong with using a calculator. You go 98.54 minus 0.2, 98.54 plus 0.2. And a lot of people get afraid, but you have to remember you're only changing this digit. That's all you're changing. That's all you're changing right here. That's the easier way to think about math sometimes, is especially if we don't have there's only one digit changing. We don't have where it's being subtracted and there's remainders between digits. So it should be 98.34 to 98.74. And a lot of problems have a little bit of leeway. Don't do this on the test. But because of a little bit of leeway, I'll have to find out the hard way. 98.34 and 98.74. I think we'll be all right. Cross your fingers. I think we'll be all right. Will we? We'll find out. Okay. Explain the meaning of the interval. I am 95% confident that the true mean body temperature is contained in the interval blank to blank. So there is 95% confidence that the interval contains the true mean. I think so. That the mean body temperature will always, no, it doesn't always fall in the interval. That the body temperature for all adults falls in the interval. Falls is a bad word. Contains the truth. Explain what 95% confidence means. 95% of 95% confidence intervals will contain the truth 95% of the time. So 95% of samples of size 52 have a mean body temperature that is in the interval. No, I'm a little worried on that. 95% of all such random samples will produce intervals that contain the truth. Yes. 95% of 95% confidence intervals contain the truth 95% of the time. More similar to what I say right here, 95% of 95% confidence intervals contain the truth. Doesn't quite say what I say, but close enough. A temperature of 98.6 is commonly assumed to be normal. Does this data suggest otherwise? 98.6 is inside my interval. So the interval does not suggest otherwise, so it contains it. The data suggests that a temperature of 98.6 is plausible. We should hopefully, unless I did rounding wrong, we got it right. There's usually a little bit of a give, a leeway on the last decimal. More accurately, because it was 0.19, that means when you subtract here, you would have this, and you would have this. That is a more accurate representation of the interval. And probably if we had gone down one further and one more away, we probably would have gotten it. No, this is very nice leeway. I'm shocked how much of a give they have on this. There we go. That's where the question gets mad at you. So you can only get so far away, but it's got a little bit of a give, like a plus or minus 0.03 or so, or 0.02. Very, very generous question. So I do like it. Really good work, really good question. And I would say this question is the majority of the chapter, hence why I do these ones slowly. It even has, what does it mean to be 95% confident? Well, 95% confidence says the law of large numbers means over the long run, 95% of 95% confidence intervals contain the truth. So the meaning of it is if you go here and you are making confidence intervals and they're 95%, over the long run, you notice your intervals contain the truth, but it's not that one interval has a 95% chance. It's that 95% of the intervals you create will contain the truth in the long run. One interval either will or will not contain the truth. Right now we have 100% of 95% confidence intervals contain the truth, but the law of large numbers states that if we keep this simulation going, we're just getting all of them. There's a 1 in 20 probability that an interval won't. There we go. There we finally got one that didn't contain the truth. Another one. So we've jumped down to 96% now so quickly. And if I keep this going, the law of large numbers shows that 95% of 95% confidence intervals contain the truth 95% of the time. It's not that one interval contains the truth. It's not that the truth will fall in the interval. The interval is what is being created right here. So you're watching intervals being created such that someone is going out and sampling people, creating intervals, sampling more people, creating interval. And if they keep doing this process, 95% of 95% confidence intervals contain the truth 95% of the time. That last 95% is not needed. 95% of 95% confidence intervals contain the truth. That one didn't. That's a fact. That one doesn't have a probability of containing the truth 95%. That one does not contain the truth. It's factual. But the thing is, you don't know this. You just know by doing the repeated process of making intervals. You'll see in the long run, if you knew the truth, that 95% of it, we had 2 in a row, 1 in 400 chance, but I know we're kind of looking for it. But 1 in 400 chance of that occurring. If we got 3 in a row, it'd be 1 in 8,000 chance. Pretty cool. I like it. Get 4 in a row, 1 in 16,000. I think 16, no. 1 in 400, 1 in 8,000, 1 in 60. Let me see. No, we'll do something else. 400. 8,000. Yeah, that's the probability of getting 4 in a row or so. Is that right? I think it's 4 in a row. It's virtually impossible. Could happen. Win the lottery sometimes, right? Let's head back to the main screen. I started multiplying the numbers and I was like, that's getting big. I was like, no way is it 1 in 1,600. And then the next one would be 3.2 million? Wow. That'd be 5 in a row. Basically, it's just super duper unlikely to see something occur in a 1 in 20 chance 5 times in a row. 2, 3, 4, 5. Yeah, 3.2 million, 1 in 20 chance. Really virtually impossible for a 1 in 20 chance thing to occur 5 times in a row. Because it's independent, that is the thing. Unless somehow there's some dependency. Okay, do another question here or two. Let's see, might do a longer one again. Oh, I do what I haven't done. Oh, I said so tired. If you have a question, put it in the chat. We'll do this one, the researcher's question. I think we are scrolled down right now. We only have 17 minutes till class. Okay, 40, 53. Mubot talking away in the chat. Chapter 14 quiz. Researchers measured. A study looked at a question. Yeah, you want to do a study looked at a question? Let's do that one instead. Here we go. Looked at, yeah, I got it right here. Let's go do it. A study looked at. What'd they look at? So a study looked at the annual compensation of 800 CEOs for which the true mean and standard deviation are known, and it gives you the true mean and standard deviation respectively. So Isha, what should we mark these? what should we mark these right here? What should we mark the true mean and the true standard deviation? What should we mark them? When you get the true mean and true standard deviation, what do you put on them in notation? True mean, true standard deviation. What should they be called? So what is the true mean in notation? What is the true standard deviation? Notice it says true mean, true standard deviation. So what are they in notation? Notation's the key to everything.
Notation, brother.
Excuse me. What would be the true mean and true standard deviation in notation? Really great to have a sheet of notation every time. Put it at the back of your notebook. That way, if I say, like, what's the true mean, true standard deviation, write it down, take notes on it. That way you can be like, oh, the true mean's this, the true standard deviation's this, because the notation won't change. Or hop over to ChatGPT. We love some ChatGPT here. Yes! Noel! It is mu and it is sigma. So notice we can go over to something like ChatGPT if we had it. Say, what is the true mean and true standard deviation in notation, mu and sigma respectively. Now, here's the thing. We learned previously that mu y bar equals mu, so mu doesn't change. Whatever, if we're looking for mu y bar in this problem, it'll be mu. The other one is standard deviation of y bar equals sigma over square root of n. So the new standard deviation will be different by a factor of the square root of n. So that's kind of the key right there, that the standard deviation gets smaller by a factor of the square root of n. So the larger the sample size we take, the smaller that standard deviation quantity becomes. So what we do right here is, if we are taking a sample size of something like 20, well, then with a sample size of 20, we'll just put 20 right here. What would mu be? Mu is going to be mu. It's going to be 10,828.75. But standard deviation is going to be 18,536.85 divided by, you got it, Noel, you said it. So we divide by whatever the sample size is, because it gets smaller by a factor of the square root of n. So all these problems right here, the easy ones are going to be the mean, because the mean doesn't change. So we're going to type in the mean right here, because the mean stays the same for the distribution of the mean. We're going to type in 10,828.75, because the mean does not change. What does change is the distribution becomes tighter by a factor of the square root of n. So we take the original standard deviation of, and go over here, 18,536.85. Well, I got to go get 30 square root. 30 square root. There's square root of 30. 18,536.85. 8 and good to see you there. There's the first one, and delete down to 2 decimals. And then we're just going to take the original, or square root of 50, and then take the standard deviation, divide it by the square root of 50. There it is right there. Notice it's becoming smaller as we increase the sample size. Divided by 10. Divide by 10 means move the decimal. So I just move the decimal, divide by 10, move the decimal back 1. And last but not least, square root of 200 is like 14.14, I think. There it is. Seen that one a few times. And we take the original standard deviation of 18,536 divide 0.85, divide by square root of 200, copy that in, paste that in here. Now, this is a simulation, and you should see the theoretical values, right? Or excuse me, these are the theoreticals close to the simulated values. So you should have values that are close, not perfect. This one's a little more off than I'd like, but no, they're, maybe I got that one wrong. We'll find out. And these are always going to be, the mean's always going to be the same, but notice how it bounces around a little bit in the simulation. The theoretical means are reasonably close. They're not going to be exactly, because simulations don't perfectly mimic reality unless you carry them out to infinite law of large numbers. And the theoretical standard deviations are also reasonably close. The simulation shows us what we would see with the theoretical values in place. So this is really, this question is just how the mean doesn't change and the standard deviation gets smaller as we increase the sample size. That's the main learning objective right here. If you look at the notes I took, It's mainly that the mean does not change. The mean stays the mean, and the standard deviation gets smaller by a factor of the square root of n. So as you increase n, the standard deviation gets smaller. And we also see that with the visualization of the central limit applet, where if you do a small sample size, it's not as tight, but the larger sample size leads to a tighter distribution for the distribution of the mean. So that's the key learning objective, is that I would say the standard deviation for the distribution of the mean gets a lot smaller as the sample size gets larger. And why is that? The central limit theorem dictates that the original standard deviation over the square root of n is the new standard deviation. So 6.22 is original standard deviation right there. And the new standard deviation is 1.25, and that would be found by taking the square root of n when we divide this. So that's the learning objectives. Once again, these formulas are something we should know and know how to read. Here's the formula with the standard error, which is the smaller version of the standard deviation. So I didn't mark that here, but this quantity here is known as the standard error of y bar. And it is showing, once again, s over square root of n. And that problem said we theoretically knew the truth, so that's why we were calling it sigma over square root of n. So really good stuff, really good kind of theory and things we should know, how the distribution of the mean becomes more normal and tighter as we increase the sample size. Any other last few questions? We did the Nabisco one, I think, yesterday. This one's the same as what we just did. We did the flight ones too, I think. Canvas content? Yeah, let's do Canvas content to end. That's probably a good spot to end on. Canvas content, let's do it. Yeah, what are you wondering, Aiden? Let me know. We also have done some full videos on it. Let me know. My eyes are just all blurry. Can't see anything today. Let me know your question. We did full office hours on it yesterday. And let me know your question. It's so rainy today. Or it was rainy. All rainy. How I know how to do it, just more of a I asked the stats question. How am I logged out of Canvas? I don't like that. I don't like being logged out of Canvas. I'm gonna stop using conditioner. It's like it goes weighing down my hair. I don't like that. Ask away with the question. Here we go. Let's go here to Canvas content. Canvas content. It's is it number 8, Noel? It's data analytics. There we go. We're figuring out if the histogram of the mean of the constant roll, how close to normal does it need to be? So really good stuff right here, Aiden. Check out the start. I'll show you this too. But because our histogram has a slight skew. Yes, check out, I'll go over and show this. Check out the very start of office hours. I'll even put the timestamps in here, but it'll be minute number 4 through minute number 22 of the start of office hours, so you can even rewind this live. But I go into the nearly normal and talk about it a little bit and show some distributions. So I can't quite tell you if yours is normal or not, but I talk about kind of with large enough n, even highlighting that in here. But talking about that, make sure it's for quantitative only though, because the other one's success failure for the first one you do for office hour, for the visualization. So check this out right here. I go into a deep dive on how to check the conditions. Yep, check that out. It'll be covered on the conditions for the T interval at the start of this office hours video. Good questions. Okay, let's do the Canvas content. Thank you, Aiden. Great questions. 50, 43, stat 201, Canvas content, number 8. Okay, here we go. Get some energy. Got Red Bull. I need to get my Red Bull. Sugar-free Red Bull today. Let's preview it. Here we go. The first question says, which of the following would you not use to check the nearly normal? Well, wait a minute. We just talked about this. Wait, Noel, what do you see in here that I said we can use to check the nearly normal? So what do you notice in here? I talk about checking the nearly normal. And which of the following, I don't know why I can't scroll down. There we go, there we go. So which of the following do you notice me mentioning? So think about which of the following do you notice me mentioning? Do you see any of the words in here? If we notice right here, I say we can use a histogram. So we can use a histogram. We can use a normal probability plot. We can also do the goodness of fit test right here. Well, the goodness of fit, you're correct. Bar chart is the wrong one. You're right. So notice bar chart was never mentioned in my talk about what we can use because a bar chart is for categorical data. So bar charts are for categorical data, histograms and such are for quantitative. So we can't use a bar chart because that's not the right kind of data to analyze the mean because means are quantitative. No matter what the shape of the parent population is, as long as our sample size is 10 or greater, we conclude that the sample distribution of the sample mean is approximately normal. This goes to the nearly normal large enough n. So you actually have pretty much all the knowledge you need regarding nearly normal right here, because this goes to large enough n. So no matter what the shape is, a sample size of 10 is large enough, true or false? No matter what the shape is, a sample size of 10 is large enough. No matter what the shape is, a sample size of 10 is large enough. No matter what the shape is, a sample size of 10 is large enough. That's so funny. False. The more skewed it is, the larger n needs to be. The more skewed it is, the larger n needs to be. So the more skewed it is, the larger n needs to be. It's so hard. I think actually if I do it this way, if I go like, I think the way to make it the hardest for this applet to do is to go like this right here. There we go. Let me do that. Man, the central limit theorem is amazing. I can still see a little bit of skew. No, you need, for extremely skewed distributions, you need much larger sample sizes. You would need, if it's very skewed, at least a sample size of 100. If it's skewed, a sample size of 25. If it's only lightly skewed, maybe 10. But I mean, like, we say skewed 25, heavily skewed 100. So the answer is false. A sample size of 10 would not work for a very skewed or moderately skewed distribution. The point of a confidence interval, don't even read what they say, is to use what's to estimate truths for what's. I'm asking a totally, well, actually very similar. The point of confidence intervals is to use what's to estimate truths for what's. The point of confidence intervals is to use what's to estimate truths for what's. Well, it's not the big number. And the question says it, no matter what the shape of the parent population is. So when we do large enough n, the first step is to look at the shape of the parent population. This is a heavily skewed parent population. So because of that, I'd like a sample size of at least 100. I don't have a sample size of at least 100, so I do not pass, or I cannot do nearly normal via checking large enough n. So this right here, we wouldn't be able to say that it meets the nearly normal via large enough n because the original parent population, the data is very skewed. And if it's very skewed, we want a sample size of at least 100 such that the distribution of the mean is nearly normal. So the large enough n goes to the large enough sample size down there, which said lowercase n, such that the distribution of the mean will be nearly normal. Exactly. If we had a larger n, the larger the n, the more normal the distribution of the mean is. And you base how large of an n you need based on the shape of the parent population, the original data. And so that's a really good question right there. So it means, you know, it says no matter the shape. No, shape matters. It matters. Confidence intervals are made from what's to estimate truths for what's. Confidence intervals are made from what's to estimate truths for what's. Confidence intervals are made from what's to estimate truths for what's. Confidence intervals are made from what's to estimate truths for what's. Well, you can see it. We drew the equation out earlier. The confidence interval is made from a sample. Confidence intervals are made from samples to estimate truth for population. So we make it from a sample. I am 95% confident the true population mean, the truth for everything. So they're made from samples because if you look at the equation has in it, no worries, we'll throw you some points right there. The equation has in it the sample mean. So does that make sense, Noel, right here? It's made from the sample mean y bar. So the sample makes the confidence interval to estimate the truth for the true mean. We're trying to estimate mu. Yeah, no worries. It's easy to get these things backwards. Confidence intervals are made from samples to estimate the truth for a population. The population is the truth, is for all data. Decreasing the sample size will make the margin of error value smaller. True or false? Decreasing the sample size will make margin of error smaller. Decreasing sample size. So the best thing to do if you got this is to write out the equation. You get them on the test. y bar plus or minus t star n minus 1 degrees of freedom s over square root of n. Decreased sample size will make margin of error smaller. True or false? Making a smaller sample size will make margin of error smaller. Well, with less data, you'd have a lesser understanding. Decreasing sample size will make margin of error smaller. It is false. It'll make it bigger. Because if you had something like 1,000 here, then you're going to have a smaller standard error. This quantity becomes smaller. But if you make this smaller, you're dividing by a smaller number, and thus it's bigger. Does that make sense? If you divide by a smaller number, dividing by a smaller number makes the top bigger. And because of that, you're going to have a larger margin of error. Theoretically, also, you'd have less data, so you'd have a greater lack of understanding. You'd have less understanding of your data. The only way to change the margin of error is to change the sample size, true or false. The only way to change the margin of error is to change the sample size. Margin of error is currently highlighted. The only way to change the margin of error is to change the sample size. Is the only way to change the margin of error to change the sample size. True or false? Yep. And the T is how confident we are. So you can change the T, you can change the sample size, that's false. So there we go. Good stuff. Good quiz. 10 out of 10. I don't know why I check. I make errors every once in a while. No matter what the shape is, sample size of 10 is large enough? Nope. Could be heavily skewed. Bar chart. Confidence intervals are made from sample sets made the truth for a population. 95% confidence interval is made, but don't worry about this question, answer mine. If I tell you a steak costs somewhere from $40 to $50, what is the margin of error? If I tell you a steak costs between $40 to $50, what is the margin of error? If a steak costs between $40 to $50, what is the margin of error? Well, 45 is the center of the interval, and the margin of error is plus or minus 5. So think what you did to find that. You have to find half the length of the interval. This is basically 60 to 70, so it's very similar to what I just asked you. So what we do is we take upper minus lower, divide by 2, and that's the margin of error, which is 4.9. So this would be like 65.8 plus or minus 4.9 or something like that. But the center of the interval is the average of the two numbers, and the margin of error is the plus or minus by which you go up and down. So it's half the length of the interval. The success failure condition for a constant interval requires what? At least 10 successes, at least 10 failures. That's for proportion intervals. No matter what the shape is, false. An employee at Guinness Beer, yep, William Gossett. Decreasing the sample size will make the margin of error smaller. No, it'll make it larger. You must have at least 10 successes, at least 10 failures. That's an interval of 15. Thus 7.5 is half the length of the interval. Oh no, what'd I do? At least, look at that. Oh my gosh. Wait, I answered at most. I said at least 10 successes, at least 10 failures. It's easy to make mistakes. When doing a confidence interval for the mean, Mr. T is mean. So when we do the mean, we do the T distribution. Which of the following is not required for testing the mean? Success failure, that's only for proportions. 74.5 to 73.7 is an interval length of 9.2. Half of 9.2 is 4.6. Hope I'm doing that right in my head. At least 10 successes, at least 10 failures. No, it'll make it wider. We'll do one more version. Did it. Guinness Beer, it is William Gossett who created it. T distribution for the mean, Mr. T is mean. Samples create intervals to estimate the truth for a population. The only way to change the margin of error is to change the sample size. False, you could change the percent confidence. And we need at least 10 successes, at least 10 failures. Yay! Are you doing pretty well, Noel? I only made one error in my multiple attempts of this, but hopefully people have it that what is not required, success failure, is for proportions. Confidence interval for the mean is done by using the T distribution. Decreasing the margin of error will make decreasing the sample size will make the margin of error smaller. That is false. It'll make it wider. Half the length of this interval, because that's the margin of error. That's 5.1, which is 2.6 when rounded. A confidence interval is made from a sample to estimate the truth for a population. Nice. There we go. Good deal. Class soon. Bye.